All right, now problem 11. So problem 11 is probably a little bit hard to understand at first, so let's read it carefully. So here we have a function f of two variables, right? And instead of finding the directional derivative in the given direction, so we are given the directional derivative and we need to find the direction, right? So the question is to find the direction uh, and the corresponding, well, actually it doesn't make sense a little bit. So find the direction and the values of the directional derivative for which the directional derivative is -1, right? So it means that the value of duf at the point -1 half and 3 half is already given. So it doesn't really make sense to ask for it because it's already given. So the answer to this part of the question we already know. So in part A, the value of the directional derivative is -1, and in part B, the value of the directional derivative is 0, right? So okay, so part of the problem is in the problem itself, but we need to find the direction uh, for which the value of the directional derivative is given. So in the part A, it is -1, and in part B, it is 0, right? And in part A, we also need to indicate the vector u and nebula f on the same xy plane, right? So it means that in part A, we kind of need to do a little sketch or plot. Okay, so let's do that. But since the question is about the directional derivative and gradients, we still need to refer to the same basically lecture as to the same part of the lecture as before. So we need to look at this theorem that tells us that the directional derivative at a point is going to be just the dot product of the gradient vector and um, and the vector u. Okay, so it is important to remember that u should be a unit vector. Okay, so let's get started. So notice that in both parts A and part B, the point at which we are evaluating um, the directional derivative is the same. So the point is, let's say P is -1 half and 3 over 2. So in both parts it is the same. So it means that essentially we just need to find the gradient vector at that point, right? So notice that again, so duf is the dot product of nebula and the gradient. So we need to find in order to do any calculation with it, we first need to find the gradient vector. And then the plan basically is to find the expression for duf in both cases. We are going to find an expression in terms of u1 and u2, and then we are going to equate this expression in part A. We're going to equate it to -1, and in part B, we're going to equate it to 0, and then we are going to solve for u1 and u2. And well, notice that by doing this, we will have one equation with two unknowns, and of course we can't really solve it uniquely, but luckily we have the second condition. So u is the direction, so which means that it is a unit vector, and for a unit vector we have the second condition, which tells us that the length of the vector u is going to be 1. So u1 square plus u2 square is going to be 1, right? So that's the plan. But first we need to find this vector nebula f. Okay, so nebula f at the given point. So it means that we need to differentiate um, f with respect to both x and y. So fx is going to be, okay, so here is our function, and it is a fraction. So we've got to use the formula for the derivative of a fraction. So it is a new fraction. The denominator is going to be just the square of the original denominator, x plus 1 y squared. Then the numerator. So first we differentiate the numerator of the original fraction times the denominator. So the derivative of the numerator is 1 with respect to x times x plus y minus. Now we've got to keep the numerator, so x minus y times the derivative of the denominator, so which is 1 with respect to x. Okay, so this is fx, so it equals, so what do we have? It is x plus y minus x, and then plus y again over x plus y squared. Okay, cool. So x minus x cancels out, and y plus y gives us 2y, right? So this is just 2y. Okay, 2y, and now I can substitute minus 1 half for x and 3 half for y. Well, I have x plus y squared, so x plus y is conveniently just 1. So squared is still 1. So this is going to be just 2 times y, and y is 3, so this is, I guess it's just 3. Okay, and fy. All right, so now in order to avoid the pain of going through all the process again, so notice the following thing. So notice that if we switch x and y, then basically the whole expression is almost symmetric. It just changes sign, right? So f of yx is essentially just minus f of x y, right? If we switch x and y, which means that when we differentiate with respect to y, what we can do, we can just switch x and y and add the minus sign. Okay, so switching x and y, we get 2x here over x plus y squared, and then we need to add the negative sign, so it is minus 2x. I mean, if you want, you can check it. Yeah, it's correct. All right, so x plus y is still just 1, so minus 2x, so x is negative 1 half, minus 2x is just 1. Okay, so nabla f at the given point is what is 3 comma 1. Okay, so should be simple enough, I think. Okay, oh, I forgot to copy the question. All right, I hope it's all right, right? So since at this point we don't really need the function anymore, so we just need our nabla f, and we need the condition that the uf is negative 1, right? So let me just copy it. Okay, so this is part A. So we already know that nabla f at the given point, which is minus 1 half 3 over 2, is 3 1, right? And recall that in part A, the question is, so find u such that du f is negative 1, right? So we need to find u. So suppose that u is, I don't know, the vector u is, say, u1, u2. Right, so then there are two conditions. So the first condition is that it should be a unit vector, so u1 square plus u2 square should be 1. And so since it is a unit vector. And the second condition tells us that the dot product of our vector u with the gradient vector should be negative 1. Right. So the second condition is, in fact, the what we're supposed to find in part A, right? So it tells us that, so the dot product of u and double f is what? So this is u1, u2, so it's going to be 3u1 plus u2. So 3u1 plus u2 should be negative 1. Right, and what we have here is a system of simultaneous equations, and we just need to solve it, right? So we need to solve for u1 and u2. All right, so how do we do this? Well, I guess the usual course of action is just to express u1 or u2 from one of the equations and substitute into the second equation. So in this case, from the second equation, it's easy to find u2, right? So u2 is going to be minus 1 minus 3u1, and then we can just plug it in back to the first equation. Right? So then we can just plug it in back to the first equation. So the first equation becomes u1 squared plus u2 is now minus 1 minus 3u1 squared is 1. Okay, so let us expand it. So u1 squared plus 1 plus 6u1 plus 9u1 squared is 1. Okay, conveniently 1 and 1 cancels out. So what I get is just 10u1 squared plus 6u1 is 0. And then I can take out 10u1. And here I will have u1 plus 6 over 10 is 0. Right, so there are two answers. u1 can be either 0 or minus 6 over 10, 0.6. All right. In the first case, if u1 is 0, then u2 is going to be, so remember that u2 is minus 1 minus 3u1, so it's going to be just negative 1. And respectively, in the second case, u2 is going to be minus 1 plus 1.8, right? So this is just 0.8. And so we found two answers. So the first answer is, the first possible u is 0, negative 1. And the second possible, okay, I guess I should write or, no, not and. So or u is negative 0.6 and 0.8. All right, and we are also required to kind of to sketch what's going on here. So then I'll try to do a little like a sketch. So I guess this is going to be like 1, this is 2, this is going to be like 1, this is 2, 1, 2, 1. All right, so this is my coordinate plane, xy. Now I need to find the point minus 1 half, 3 over 2. So the point, and then take a different color. So the point at which we are considering everything is somewhere here. And so this is our point P. And so this is minus 1 half, 3 over 2. And so this is right P. Okay, so then we need to indicate our two vectors, 0 and negative 1. So 0 and negative 1 is so along y it is 0 and along x it is negative 1. So I guess, no, stop, 0, negative 1. So along x is 0 and along y is negative 1. So it looks like this. All right, so this is 0, negative 1. At the point P, so the second vector is going to be minus 0.6 and 0.8. So minus 0.6 is, I guess, somewhere here. 0.8 is somewhere here. So it's probably something like this. So this is minus 0.6 and 0.8. So these are the two possible vectors u. And we also need to indicate the gradient vector on the same plot, right? So let me take yet another color. And the gradient vector is 3, 1, right? So it is 1, 2, 3, 1. So this vector. This is nebula at the given point. So this is the schematics. So notice that, of course, because of the geometry, basically these angles should be the same. So the two vectors that we found, they are symmetric about the gradient vector. Right? So this is part A. All right, part B is somewhat easier. So in part, stop, problem 11. So I guess it's going to be problem 11B. Okay, so in problem 11B, we still know that nebula F at a given point is 3, 1. Right, but what we need to do is we need to find the direction vector such that the derivative, um, the directional derivative at a given point um, is zero, right? Now, but then it means that the dot product of our vector, so the gradient vector, which is 3, 1, the dot product with u is zero, right? So what does it mean? It just means that these two vectors are perpendicular. So geometrically they're perpendicular, and at the same time, you know, the equation that we have is 3u1 plus 1 times u2 is 0. And basically, it's easy how you can satisfy this equation, right? I mean, so you have numbers 3 and 1, so you just need to flip them around and replace them with one of them with a negative sign. So I mean, you can write -1 instead of u1 and 3 here, and it's going to be -3 plus 3 is 0. Or you can write 1 here and -3 here, right? And then you're going to get 0. So these two candidates, -1, 3, and 1, 3, so they're just directly opposite each other, right? So basically, they are one of them, looks into this direction, so the other one in this direction, so they're just opposite of each other. So which kind of makes perfect sense. So these are going to be our two answers. So the only thing that we need to do, we need to normalize them because we are looking uh, for a unit vector, right? So instead of, we can't just write -1, 3 because the length of that vector is not 1, right? So we need to divide by its norm. So we need to divide by the square root of -1 squared plus 3 squared in both cases, and this is just 10. So the answer is going to be -1 over square root of 10, 3 over square root of 10. It's the first one, or 1 over square root of 10, and stop, -3. -3 over square root